In the last lesson, we sorted out something important about the hyperbolic function. Let me remind you. This function has the form y equals a over x plus q. We chose to use y equals 1 over x as our parent graph. In other words, we used an a value of 1 and a q value of 0. We plotted this graph from a table of values. We saw that this graph has the x-axis and the y-axis as asymptotes. That means that the graph never crosses these two lines, although it gets closer and closer to them. Now we want to see what happens to this parent graph and its asymptotes if we change the value of a or q in the formula. By the end of this lesson, you should be able to describe how the value of a and q affect the graph of the function y equals a over x plus q.
You said we're going to see what happens when a and q change in the function, right? But that sounds a bit complicated. I mean, that's a whole lot of changing.
Don't worry, we will take it slowly. And to start, we are only going to change the values of a. That means we will make q equal to 0 for now. Are you ready to try an example?
I'll give it a go.
What do you think happens to the graph of the function when a equals 4 and q equals 0?
I don't know.
That's okay. Let me help you. I've already made a table of values for this graph and plotted the coordinates from that. Have a look.
But it looks the same as y equals 1 over x, doesn't it? What's the difference between this graph and the parent graph?
Sure, the shape looks the same. And the graph still doesn't cut the axes, and it appears in the first and third quadrants of the Cartesian plane. But let's compare this graph with the parent graph to see if they are the same. Here is the parent graph again, so that we can discuss how changing a to 4 changed the graph.
Oh yes, now I can see. The graph with a equals to 4 is sort of pulled away from the axis. Is there a better way of describing this change?
You are talking like a real mathematician. Have a look at the formula of each graph. What makes the two formulae different?
The 1 and the 4 are the only difference. That's the a values.
Right. So the change in the graphs must be because of the change in a from 1 to 4. This means that the y values have become 4 times bigger on the new graph. Look here. When x is 1, y is 1 on this graph, and y is 4 on this graph. So the y value is 4 times bigger. When x is -1, y is -1 on this graph and -4 on the new graph. This time the y value is actually 4 times smaller on the new graph.
So, it's like every point on the parent graph has moved vertically to another point on the new graph, which is 4 times the value of the old graph.
Yes. Let's just describe that a bit more accurately. Each point on the parent graph has moved to a point on the new graph that has a y value that is 4 times the original y value. Have a look at the formula for this graph. It is y equals 4 divided by x, but we could write that differently. That is the same as y equals 4 times 1 divided by x. In other words, 4 times the parent graph of 1 divided by x. I will leave it for you to check this fact out some more. Use another graph, say y equals 3 divided by x, and compare y values on the parent graph with y values on the new graph.
Let's try another one. Maybe this time we should choose one that has an a value less than 1.
Great! That is a good plan, because then we can compare the graph with the a value less than 1 with the parent graph and with the graph where a is 4. Why did you choose an a value between 0 and 1?
That means a must be positive, but smaller than 1. What about a equals to a half?
Okay, then the formula would be y equal to a half divided by x. Here is the table of x and y values for this graph. Plotting the points in the table would give me this graph. Now let's compare it with the parent graph. Here is the graph of y equal to a half divided by x compared to the graph of the parent graph. Is that what you thought it would look like?
Sort of, I guess.
See if you can describe the changes that the a equal to a half have made to the graph.
Well, the graph still has the same shape. It doesn't cross the axis, so there's still asymptotes again. It is still in the first and third quadrants of the Cartesian plane.
That's great. Anything more?
Yes, the graph lies closer to the axes.
That's right. Let's look at the graph of y equals 4 over x again and see if what we learned from that graph can be applied here. Each point on this graph had a y value that is 4 times the y value on the parent graph. This is also true about the graph with a equal to a half. Each point on the new graph has a y value that is half of the y value on the parent graph. Have a look. -1, -1 on the parent graph becomes -1, a half on the new graph. And in the first quadrant, we take 1, 1 on the parent graph. It becomes 1, a half on the new graph.
I think I've got it. Each y value on the graph y equals to half over x is half of the y value on the parent graph.
Right. There's another change to the a value that we need to consider. What do you think will happen to the parent graph if a is negative?
I haven't thought of that. I think it would be some kind of reflection of the positive graph.
Let's check that. I'm going to choose a equal to -1 first, which gives us the formula y equals -1 over x. And the graph of this function looks like this. It lies in the second and fourth quadrants. Is that what you expected? Let's compare this new graph with the parent graph. Can you see what happened here?
Yes, I get it. If you were to fold the whole plane on the x-axis, then the new graph would fall onto the parent graph exactly. The part in the second quadrant would now be in the third quadrant. The part in the fourth quadrant would now be in the first quadrant.
Well done. Let's put all the things we have found so far together. We have compared the parent graph y equals 1 over x with 3 other graphs that had a equal to 4, a equal to a half, and a equal to -1. We found that if a is bigger than 1, the new graph made is pulled away from the x and y axes. And if a is smaller than 1, but bigger than 0, the new graph lies closer to the axes than the parent graph. We also found that for positive values of a, the graph of y equals a over x has 2 parts, one in the first quadrant and one in the third quadrant. For negative values of a, the graph of y equals a over x is reflected about the x-axis. It has 2 parts. This time one part is in the second quadrant and one part is in the fourth quadrant. We started this lesson by saying we want to investigate the changes in A as well as in Q are functions of the form y equals A over x plus Q. We have seen the effect of A. Now we need to study the effect of changing Q. To make things simple, let's keep the value of A at 1 while we change the value of Q. This will make it easier to study the effect of changing Q on the parent function y equals 1 over x. Then, to get the full picture, we will also look at the effect of Q on the graph of y equals negative 1 over x in the second and fourth quadrants.
Wait, I think I can already make a conjecture about the effect of Q.
Great, let's hear it.
Well, think about the other functions. The straight line graph shifted up and down the y-axis when we changed the Q value. The parabola did the same. The Q in both these graphs shifted it.
Carry on. You are onto something here.
I think if we increase the Q value, then the graph will shift up by Q units. If we decrease the Q value, then the graph will shift down Q units.
Did all of you watching follow that reasoning? Let's see if this makes sense on the graphs. I have prepared several graphs for us to look at together. First of all, here is the parent graph again. The formula of this graph is just y equals 1 over x. So the Q value is 0 on this graph. If I change Q to 1, I get a new graph for the formula y equals 1 over x plus 1. Do you see how the whole graph has moved up 1 unit? Because the whole graph has moved up 1 unit, this asymptote also moves up by 1 unit. It is no longer on the x-axis. The other asymptote, which is on the y-axis, stays the same. If I change Q to 2, I get this graph. The formula is y equals 1 over x plus 2. The whole parent graph has shifted up by 2 units. Again, the asymptote moves up by 2 units, but the asymptote on the y-axis remains the same. Let's now decrease the value of Q. Check carefully how the points on the graph move.
If we make Q minus 1, then the whole parent graph shifts down 1 place.
So it looks like you were correct. As the value of Q increases, the parent graph shifts up by Q units. As the value of Q decreases, the parent graph shifts down by Q units. We can summarize the effect of Q on the graph like this. A change in Q causes the graph of y equals 1 over x plus Q to shift up or down. If Q is positive, the parent graph shifts up Q units. If Q is negative, the parent graph shifts down Q units.
But how is this different from what you saw about the effect of A on the graph?
You have asked a very important question. When you use a positive Q value greater than 1, the negative part and the positive part of the graph are both shifted up. You don't have the graph pulling away or moving closer to the axes.
Oh, I see now. A changes the shape of the graph and Q shifts the parent graph without changing the shape.
That's correct. I'm so glad that you have got it. And although we have looked at several graphs of hyperbole in this lesson, it's not enough. You need to go and test our findings on other hyperbole. Don't just accept what we have found. Now it's time for some tasks. Today we have 2 tasks for you. 1. Compare the parent graph y equals 1 over x with the graph of y equals negative 4 over x. How has the change of the value of A affected the graph? 2. Compare the parent graph y equals 1 over x with the graph of y equals negative 1 over x plus 2. How has the change of the A value and the Q value affected the graph? Remember that practice makes perfect. So keep working with all the graphs that we have studied so far. In our next lesson, we will compare the effects of the a and q values across the three types of functions, linear, quadratic, and hyperbolic with each other.